give you the big picture. We've got 3 weeks until your exam, and so we're going to do the following.
For Christmas break.
I know, isn't it wild?
4 weeks.
Yeah, yep, exactly. So what happens is we have this week, we're going to finish up chapter 4. We're going to do some antiderivatives and definite integrals. And then we're going to continue that next week. Week following, we'll have 1 or 2 days of review. And then your exam will be either on the 19th or the 20th of December. I have to negotiate with the other AP teachers to figure out exactly what. So, first item. Currently on Edmodo, you're scheduled to have a test on Chapter 4 on Wednesday. I understand you're going to be on the New York trip. Are you on the New York trip? Anybody else on the New York trip? You're on the New York trip.
Good job.
Okay. Then let's do this. We're going to move our test date to Thursday. And the upshot of that is that we are just going to do a little bit more with the antiderivative stuff that we're doing. Antiderivatives will not be on your test. It's kind of weird. Your book actually does antiderivatives in chapter 4 without telling you that it's doing antiderivatives. And I find that a very strange presentation. Report them, that's right. I find that a strange presentation. So we're going to do antiderivatives as a bridge between chapter 4 and chapter 5. And we're going to invoke the mean value theorem to justify what we've done with it. Okay? All right. Also coming soon is going to be a chapter 4 or a theorems project. And the due date is TBD. Yes. The interesting point of discussion is that doing it will help prepare you for your exam, but it's going to be a lot of work also. So I want you to think about. What's that? Last year I did it in pairs, and I could let you guys work in pairs. But if I do, then we're going to have to circumscribe how that goes, just to make sure everybody's pulling their weight. Okay. Okay. Next thing, you had some homework over Thanksgiving, so go ahead and get that out and turn it in at this time. All right.
We have homework? No, I just came back from after during the 11 p.m. I want a chance to pick up the movie.
Last week, 2 Mondays ago, it was supposed to be.
I don't remember.
Thank you. Good. Good. Very good. Danielle? How much do you have to do?
I have 2 left.
2. Okay.
Last night. I don't know. It's a Friday's homework, right? What?
You know what? All right. Let's talk antiderivatives. So here's an interesting question. We can consider it derivative jeopardy. Have all of you watched the Jeopardy television show? And you know the format of the show. We give you the answers. You tell us the questions. Okay? Well, this is exactly the same kind of a thing. Here, I'm going to tell you the answer. F prime is equal to cosine of x. Now the question is, what was F?
Oh.
Minus.
Ah, y plus c.
Is the derivative of the C is zero. Like, yes.
Could be any one of these, because all of these have a derivative of cosine x. But now here's an important question. Could f be some other function also that is not in the form sine x plus c? Could there be some function out there that's not in the form sine x plus c, whose derivative is also sine x and cosine x? She thinks no. How many of you think possibly? How many of you think no? Well, your choices are either possibly or no, or yes, if you have an example. So let's do this vote again. How many of you think no? How many of you think possibly? Josh, you got to vote.
Sorry, no.
You think no? Okay. I claim no. To get there, we're going to have two simple short theorems. First, I'm going to show you that if a function has a zero derivative, it has to be a constant. And then, from there, it's a simple jump to say that if a function has a given derivative, it is unique within a constant. So, here's our zero derivative theorem. Now, it's very particular. If a function has a derivative of 0 on a closed interval, a to b, then f of x is a constant on that closed, I should say closed and bounded interval, a to b. Now, the proof is really cool. The proof is going to use an idea that we basically call a bump principle. And what I'm going to show is that that f of x cannot have a bump. Here's an example of an f of x that has a bump. And I'm going to show that it's not possible for f of x to have a bump if its derivative is always 0. Okay? So, the proof is going to be a proof by contradiction. Suppose that f of a is equal to c. I'm going to just assign f of a is equal to c. And suppose that there is an x in a to b such that f of x is not c. Okay? So we're supposing those two things. Now, here's where we're going to appeal to the mean value theorem. First of all, let's check. Does our function satisfy the conditions of the mean value theorem? Is it continuous on the closed bounded interval a to b? Is it differentiable on the open interval a to b? Well, what do we know about f? We know only one thing. F prime is equal to 0 on the closed interval a to b. So is it differentiable on the open interval a to b? Yes, definitely, because that's a subset of closed interval. Is it continuous on the closed interval? Yes, because it's differentiable. Ah, so it satisfies the conditions of the mean value theorem. And so we can say that there is a C. Conditions of the mean value theorem on what interval? Let's be careful here. What we're doing is we're supposing that our bump occurs somewhere at point X. And so we need to apply the mean value theorem on the interval from A to X. And X could be B, but it doesn't have to be. So there is a C somewhere between A to X, such that f prime of C is equal to f of A minus f of X all over A minus X. It's actually the other one, f of X minus f of A over X minus X. No harm in writing it either way. This does it in numerical form. Okay? But now, what we supposed is that f of X does not equal C, which is f of A, which means that this quantity, f of X minus f of A, has to be equal to something other than 0. Which means that f prime of C is not 0 on this interval. But wait a second. What is the condition that we had on f prime to begin with? It was 0. This is a contradiction. Therefore, we conclude that a bump is impossible. Now, often when you do a proof by contradiction, it's possible to turn it around and make it a direct proof. And so we're going to do that at this time. So we're going to simplify our proof a little bit. By applying the mean value theorem to any x in A to B. Not including A, of course. Actually, let's put it to any interval A of x, where x is in. Then we have f of x minus f of A over x minus A is equal to f prime of C, some x in A to C in A to x. And since f prime is equal to 0, we conclude therefore that f of x minus f of A must be 0, which means that f of x is forced to equal f of A. And this is a way to simplify the proof here and conclude that f of x has to take on the same value as f of A. In other words, f of x is bumpless. Now, from this, we can immediately conclude that functions that have the same derivative are the same function within a constant. This is our derivative jeopardy theorem. If f prime equals g prime on the interval A to B, then f equals g plus a constant on the interval A to B. And the proof is delightfully simple. What we want to do is to leverage our zero derivative theorem. So we need a function whose derivative is 0. And so we're going to introduce a helper function. We're going to let h of x be the difference between f and g. And since f prime is equal to g prime, h prime, which is f prime minus g prime, is identically equal to 0 on A to B. But this immediately forces h to be a constant. so that f minus g is a constant. So that f is equal to g plus that constant. Now what is the upshot here? The upshot is that if I give you a derivative, then its parent function is a unique function within a constant. Yes?
So, h has to be a constant
Because its derivative is 0. That's why
okay.
we got it in there. Yep. And that's where we're using our zero derivative theorem. So I'm going to introduce a piece of notation that your book does not introduce until later, for reasons I do not understand. And the piece of notation is this. If g of x is a derivative of some function f, then we can say that f of x is equal to the antiderivative of g of x dx plus a constant c. Or actually, a better way of putting it, honestly, is to write the constant c on the other side. There we go. And all that I'm doing here is I'm taking our previous theorem and I'm putting some notation to it. This operator, the integral dx, is an antiderivative operator. It undoes the derivative operation. Now, you may say, that's kind of a funky notation. Where did that symbol come from? Why do we use it? So on and so forth. I'm going to ask you to suspend that question for about 3 days, so we get past our chapter 4 test. And then once we, actually until next week though, and then once we do some Riemann sums and so on and so forth, then the rationale behind the notation will make a whole lot more sense. For now, just accept it. This thing means antiderivative. What's that? It uses this symbol, it just waits until chapter 6 to introduce it, which is weird. What's that? So chapter 5 in your book has to do with definite integrals, and it builds up definite integrals first, which is a totally legitimate approach. But it introduces in section 4.2 this concept of antiderivative without calling it that. So it does exactly what we do here. We've got the 2 theorems, the zero derivative theorem and the what I call the derivative jeopardy theorem. It just doesn't give you any notation for it, which is a strange thing. So I'm giving you the notation. So in terms of our notation then, we would say that the antiderivative of cosine x, spelled like so, is sine x plus an obligatory constant c. Obligatory means you must put it. Don't forget it. Okay. Now, what is the meaning of c here? And what is this telling us? Here's one way to think about it. If I have f prime is equal to cosine x, then the functions sine x plus c form a family of parallel curves like that. If I let c equal 1, that corresponds to a vertical translation by 1 unit. If I let c equal 2, that corresponds to a vertical translation by 2 units. And what you can see, no pun intended, is that all of these different functions right here are going to maintain a constant distance from each other, like that. In other words, they are parallel curves. Oh, interesting. Why are they parallel curves? Because they all have the same slope. That's pretty cool. So these functions here, sine x plus c, are a family of curves. And this family of curves is defined by being parallel. We call c a parameter, in other words, a constant, that defines the various members of the family. And what characterizes each different member of the family is its vertical height, right, or its vertical translation from origin. So if we want to identify a particular member of the family, what we need is an additional piece of information besides just the derivative. Exactly. We need to know one point on the graph, and just one point will do it for us. So an implication or a corollary to our derivative jeopardy theorem is that this differential equation an equation in terms of the differentials dy and dx, this differential equation with an initial condition has a unique solution. So we can think about an antiderivative as a tool for solving differential equations. Not the only tool, but a powerful tool.
I'm sorry.
Uh-huh.
That's corollary.
Oh, a corollary is a short, easy theorem that is a consequence of something you've already proved.
Oh,
So it's like a one-step theorem.
okay.
Yep. So the proof of this is where the proof is just like obvious. You just think about it. So since our derivative jeopardy theorem guarantees that two functions with the same derivative are the same function within a constant c, it therefore follows that if I have a differential equation, the derivative equals the function, and I have the initial condition right here, then antiderivative gives me the function, the family of functions. There's only one of those that will pass through the point x0 to y0, and we're done. So let's just show some examples. This is the typical derivative jeopardy kind of question. We are given a differential equation or a derivative, and we are asked to find, we're also given an initial condition, and we are asked to find the function y of x. Okay. So, we're going to express our solution as an antiderivative. Now we run into an interesting puzzle. The derivative rules are pretty mechanical. I give you some. What's that? Ah, very good. That's right. So, the antiderivative right here, I'm not going to be able to follow a rule. Instead, I'm going to have to recognize derivatives when I see them. And that's exactly what Jackson did. Very good. So that we have the antiderivative of secant squared x dx, which is tan x plus c. Okay. Now, to find the particular c, we can call this the general solution. It gets us into the right family of functions. Now we can find the particular solution by appealing to the initial condition. When x is 0, y is 4. So that 4 is equal to tan of 0 plus c. What is the tangent of 0?
0.
So that c is equal to 4. Is c always equal to the initial condition? No.
Oh, yeah.
No.
No.
I mean, in this case.
In this case it is, but it is not always equal to the initial condition. We have to actually plug in and find out. And so therefore we package our final answer as y equals tan x plus 4. This seems really simple. And when Newton first discovered it, and Leibniz discovered it also, initially the thought was, we're going to be able to basically solve everything. Then people started to play around and discover that finding antiderivatives can be hard. So, part of our task, a big picture goal for us, for the months of December and January, is to get better at finding antiderivatives. And unlike the derivative rules, where we're going to walk through and have it be mechanical, here we're going to have some antiderivative rules. We'll cover most of those tomorrow, maybe today. But those antiderivative rules are going to be more like moves that you can make rather than a mechanical process for finding every single derivative. Does that make sense?
Yes.
In other words, finding antiderivatives is much more like a puzzle than finding derivatives was. Let me show you some moves that we can make. Let's talk about a few basic antiderivative rules. Okay? And we're going to derive all of these from the corresponding derivative rules. Let's get ourselves a constant multiple rule. The antiderivative of kf of x should be the same as this is not even
No.
Yeah, k times the antiderivative. Okay. Now, why is this? How would the proof go?
It's a constant.
It is constant. So what?
Just like derivative.
Okay, so we would get it somehow from the derivative rules, right? So what we have to do then is to show somehow that the derivatives of these two things are equal, and therefore the two functions are equal within a constant, which is packaged in. So let's take the derivative.
fx equals g prime.
Yeah, that's exactly it. When I take the derivative of the antiderivative every single time, I get the original function. Okay? What about this stuff?
So it's k times the antiderivative. So it's the same.
We get k, using the constant multiple rule for derivatives, k times the derivative of the antiderivative
So it's
cancels, gives us our function back. We conclude that the two functions have the same derivative, therefore they are the same function within a constant, and the within a constant is understood here. Does that make sense?
Yes.
Okay. What other derivative rules might we wish to come up with?
quotient
Quotient rule, yeah, that'd be pretty advanced.
or power.
Power rule, all right, let's do that. What is the derivative, the antiderivative of x to the n? I need to work backwards from my power rule for derivatives. What's that?
X.
1 plus 1.
No, n minus 1 times x.
N plus
What's the derivative of x to the n?
N x to the x minus it.
To the x minus 1?
I don't know, n minus 1.
N minus 1, okay. So if I'm going to work backwards from here,
It would be
x n plus 1 over n plus 1.
there we go. And don't forget your obligatory constant c. Now let's check that. How does our proof go?
derivative of the antiderivative with x.
Mhm.
The operators cancel out.
Yeah. All right, now what?
Derivative of x
Mhm.
to the constant over n plus 1 plus c.
Yeah.
So it's derivative of the first one plus derivative of constant.
Mhm. All 0.
So it's x plus 1 times, oh no, over x plus 1 x squared. So cancel out x squared.
Okay, let's make that happen more systematically here. The 1 over n plus 1 is a constant.
Yes.
Comes out.
Oh, yeah.
Okay. The derivative of x to the n plus 1 using our power rule.
X plus 1.
Not x
No,
plus
no.
1.
X to the n.
Okay. The derivative of x to the n plus 1 is not x to the n. The
It's
derivative of
x plus 1 times x to the n.
there we go.
You tell me.
That gives me x to the n. Yeah, gotta think about that. Think through that carefully. Speaking of thinking it through carefully, can you imagine any n's that would break our power rule? Mm-hmm. Exactly. So we have to put a condition on this that n is not -1, because if n is -1, exactly -1, then we will end up dividing by 0, which is ridiculous. Right? Well, speaking of, I wonder what the integral of x to the negative 1 power would be. And to get at that, we can rewrite that as 1 over x, and we observe that we get natural log x plus c. Now, this takes a little bit of interesting special care and feeding, because we have, for the first time, a little bit of a domain puzzle. What is the domain of the function f of x equals 1 over x? Yeah, that's right. All real numbers but 0. But what is the domain of g of x equals natural log x?
Only positive.
Only positives. That's exactly right. Huh. This is a really interesting puzzle, because what we have here is a function that is differentiable for all x not equal to 0.
You forgot the absolute x.
Well, I did, but I'm going to need to come back and argue for it. You're exactly right. It turns out that this C right here, within this C is packaged a world of interesting mysteries. And we're not going to be able to unpack all of these mysteries until February, when we've done some infinite series. We're going to find out that the value of the C right here can actually be a complex number. And that complex number can lead us to an interesting representation for natural law. So here we're talking about like calculus with imaginary numbers and so on. So rather than going to that whole thing right here, let me suggest a quick fix, the one that Danielle suggested. And that is that if I have a slightly different function, g of x equals natural log of the absolute value of x, that function now has a domain of all real numbers except 0. And when I take its derivative, I get 1 over the absolute value of x times the derivative of the inside. Would you look at that? The derivative of the natural log of the absolute value of x is equal to 1 over x. Ooh, that's interesting, because that means, since these two functions have the same derivative, that in some sense the natural log of the absolute value of x is the same as the natural log of x plus c. Which is interesting and weird, because it means that somehow it's possible to take logs of negative numbers. But when you do, as it turns out, you get imaginary values as your result. Okay, leaving all of that aside, we want to take this as our basic antiderivative rule. The antiderivative of 1 over x, we're going to take as the natural log of the absolute value of x plus c. And that will accommodate both the positive domain and the negative domain. Does that make sense to everybody? All right, well, let's see. What derivative rules do we have so far? We have a constant multiple rule. We have a power rule. We have a special case 1 over x rule. What other?
Chain.
Chain rule. Yes. Wednesday, substitution. We're going to start in on chain rule. So let's hold off on the chain rule. It's going to be delightful.
Yeah.
Yeah. How about a sum rule? And is?
Antiderivative of f plus the antiderivative of g.
Can you prove that loud?
Take the derivative of the antiderivative of f and g,
Mm-hmm.
then take and then that equals f plus g.
Mm-hmm.
Then take the derivative of f, give x plus the derivative of the antiderivative of g, does some rule of derivatives.
Yep.
And then you get f plus g again.
Good. Very good. So immediately from that, we would also get a
Difference rule.
and then there would be no difference rule. Let's see, where else would we want to go? A quotient rule, right? Before quotient rule, probably product rule. The product rule we're going to call integration by parts, and we're going to spend some time on that. What's that? We haven't already done product rule for antiderivatives. We did it for derivatives. And we're going to call that integration by parts. A quotient rule is probably going to be a real pain. And generally, there is a quotient rule for antiderivatives. I've never seen it used in what? It would go like this. The integral of fg prime minus gf prime, excuse me, minus fg prime all over g squared equals f over g plus c. And the odds of you finding and successfully recognizing gf prime minus fg prime over g squared are kind of small, right? It's unlikely that you're going to end up in a function in this form. So a quotient rule for antiderivatives does exist, not very useful. The product rule, not so much. The product rule we're going to like. It's going to take the form that you would expect right here. But really what we're going to do is we're going to rewrite it in a manner that is going to allow us to take things in the form fg prime and rewrite them as fg minus the integral of gf prime. That's the spirit of integration by parts. It's going to be a really powerful tool for us. Let's see here. What other antiderivative rules would we have? Yes, we're going to have all the trig functions, and they're going to be written like this. The integral of sine is negative cosine plus c. Why? Because the derivative of cosine is negative sine. Watch that negative sign right there. Students love, and even teachers, love to forget that negative sign. The integral of cosine is sine. The integral of secant squared. Wow, that was the worst integral of sine I've ever done. The integral of secant tangent. And the integral of cosecant. Negative. Cosecant.
Huh? Oh, okay.
But there's a big hole in our chart. What functions don't we have antiderivatives for yet?
Negative. No. Like,
Well, right, we don't have antiderivatives for inverse trig functions, but more basically, just looking at the trig functions. What
tangent.
Right. I don't have an antiderivative for tangent, or secant, or cotangent, or cosecant. Out of the 6 basic trig functions, I don't have antiderivatives for 4 of them. We need to fix that. We're going to fix that over there.
Like, this will be like the test on Thursday.
Antiderivatives will not be on the test.
Okay.
Wait, do I have a paragraph there?